All right, so get out your notes. Make a heading for a thing called molar volume. Make a heading called molar volume. So, notes. You got your notebook, Keegan? Henry, where's your notebook? Get out your notebook. We're doing notes. Ethan, you got your notebook? Notebook? All right, so make a heading called molar volume. Now, molar volume is a really easy concept at this point. We're going to tease apart more complexity when we get to the gas unit, but for now, we're just going to add a tool for Stoich that deals with volume of a gas. That's it. That's all for today, for this unit. That's all you need to understand. Molar mass has molar volume has a definition. You're going to want to write this down, and then we're going to talk about what it means. A gas, 1 mole of a gas, at STP, which we'll talk about briefly, will occupy 22.4 liters of volume. And there's some assumptions in here, but again, we're not going to really care about those for now. We're going to kind of take this at face value for the sake of putting this into a T-chart, is essentially what we're going to do. And I want you to think about the parallel between molar volume and molar mass. Right? How did we use molar mass in T-charts? What's that? That was kind of connected to that. What was yours? Yes, what, though? Molar mass. How did we calculate that? Yeah, we use that as two things that are equal, right? We said a mole of something is equal to some number of grams of something, right? That was molar mass. Now, yes, the Avogadro's number was tied to that. But ultimately, if we're talking about a gas only is where this works. So something like carbon dioxide, something like sulfur dioxide, something like carbon monoxide, something like oxygen gas or hydrogen or nitrogen, something that's diatomic would work for this. Okay? So this becomes another equivalent that we can use in a T-chart. So let's do that. Need to make my pen live here. So write down this problem in your notes right underneath that definition for molar volume. And we'll do this one together. How many liters does 14.3 grams of CO2 occupy at STP? STP stands for standard temperature and pressure. So if you think of a gas, right? If you had 22.4 liters of some gas and then you squeezed it down, well, you could make it any volume you want if you change the pressure. So we're going to say standard temp and pressure. And again, we're going to learn what that means and how to manipulate that in the gas laws. For now, we're just going to take that as an assumption, standard temp and pressure. So let's make a T-chart. What are we going to start with on our T-chart? 14.3 grams CO2. Okay, what can we do here? Grams to moles, yep, molar mass. Grams of CO2 is going to be 12 plus 36, 44. Copy down our units. And now here is where, again, with T-charts, what are we trying to get to? What is the question asking us for? Yeah, it's asking us for liters of a gas. Well, we now have what you just wrote down in your books. We now have an equivalence that we can use. 1 mole of a gas is equal to or liters of CO2. The rest of this is just math. So when you do the math, it's going to be like 7 or 8 or something. You don't have to. Answer would be liters of CO2. So that's it. That's the whole kit and caboodle for this particular concept. It just gives you another box, another way to manipulate conversions in a T-chart. That's it. That's all we added. That's the additional layer to this. T-charts don't change. You just now have a way to express a gas in liters. Which again, volume of a gas generally is an easy way to measure gases. So get out your worksheet packet real quick. Go to the page that has, I guess it's the the third page in this. The top says Stoic with Avogadro. I want you to circle question 3 and all of them on the back. 1, 2, and 3 on the back of that one. That's the homework for today, but we're not done. Number 3 on the front. This page, yes, number 3. And then all of them on the back. So page 3, the third page in your worksheet. Number 3 on the front, and 1, 2, and 3 on the back of that. And then turn your worksheet packet to the 4th page. Just turn to that page where it says heat and stoic. Put a new section in your notes called heat and stoic. Oops. We are going to add another concept to your T-charts and to equations. Now, we've done heat before already. We've talked about endothermic and exothermic reactions. We've already done this. We understand the concept. What we're going to add to this is how we notate that in an equation. So the first equation we're going to use is my favorite. We're going to talk about adding hydrogen and oxygen together. But you'll note, obviously, a difference on this equation is written. What's different about this from the other 43 times we've used this? Yeah, what is this joules thing? Kilojoules, 518. I've seen this equation. Clymer, you've written this down 100 times. But you've never put on here kilojoules. So when you perform this reaction, have we done that in class? Have we lit some hydrogen on fire? Well, I mean, we tried it with the egg thing. It worked. Kind of. It worked. I wouldn't say it didn't work. So, when you do that, when you light hydrogen on fire, how would you describe that reaction? What happens? It explodes. I agree with you. Depending on the amount of hydrogen, more or less of an explosion. But what is released when we make that reaction happen? What's that? Light. Heat, light, yes. Energy. This is that energy. Why is it on the right on this equation? What's that? Yeah, so you have the products, right? And you also have some amount of energy. Your product here was water. and you also got some energy. If we flipped this equation around, what would that look like? If we instead wanted to decompose water, what would that look like? Do we get energy out of that? What did we have to do to decompose water? Do you guys remember this from day 2 or whatever? We had to add energy in, right, with the electricity? We did hydrolysis.
Yes, sir.
We separated, or electrolysis rather, we separated those things, but we had to add energy to do that. So if you flip this equation around, you'd have the H2O on this side, and you'd add energy to it. And then on the right-hand side, your products would just be water, or you would have hydrogen and oxygen. So let's see if we can do a Stoich problem with this concept. You're writing this down in your notebook. How much energy is released if 40 grams of hydrogen is used in the the above reaction? Got a little crazy with the eraser. I blame Henry.
Okay.
So this is going to be another T-chart. What are we going to start with in our T-chart?
40 grams of hydrogen.
So here I am at this step. What do I do from here? So far, this is just a pretty standard looking T-chart. Start with grams of something, use molar mass, get to moles of something, but now what? Now I've got this equation up top with energy in it. I'm at moles of hydrogen. What do you think would go top and bottom here? The 2 here. What about up here? I agree. Do some math. 40 times 5 is 2,000 divided by 4 would be, it's going to be 5,000-ish. $51.80. Well, duh, yeah, 4 divided by 4. Now here's the brain teaser. What is the sign on this energy number? Is this a positive or a negative? Remember, we're talking about heat here. We're talking about endothermic and exothermic. What's the sign going to be here? Why negative? Yeah, this is being released. This is energy leaving the system, right? This would be a negative energy. This is an exothermic process. But again, just like we had in the molar volume thing a moment ago, what we added was simply a relationship here that we can use in a conversion. So let's do one more example together. So try this one. Write this one down. Now please note, this is not the same equation from above. It's the same but different. How is this equation, as written in this problem, how is this different? What are we doing this time with the water? Yeah, so we're trying to decompose water. We're trying to break water apart. So how will your equation here differ? True. So this is an endothermic process, yes. Ah, how is your equation going to look then? Yes. So our equation is a little different this time, right? Same bits and pieces, but we have to rearrange them because now we're not creating water, we're decomposing water into what it's made of. So your equation here, your reaction is a little different. And you're right, because we're putting energy in here, you're putting energy into the reactant side, your kilojoules will move to the left. And then to solve the question, now what do we do? What do we start with in our T-chart? And then mole. So water is 18, is 1 mole. And then what is the last box of my T-chart going to look like here? Again, this is kind of a mismatch of your molar ratio, right? Where in this equation, 2 moles of H2O is equivalent to 512 kilojoules. We do the math. We come up with 9195 kilojoules. And then now again, now we have an energy number. We need to be careful of the sign. What kind of process was this, endo or exothermic? Endothermic. What will our number be in our energy? Will be positive energy. That is heat and stoich. Mr. Helgeson?